Okay, let's get started. We are going to start off today talking about deliverable 6, which is due tonight, and I will introduce and walk you briefly through deliverable 7, which is now on Blackboard, and you can get started at any time. And when we finish with deliverable 6 and 7, we'll hop back to lecture 9 on information spaces. Okay, let's start with deliverable 6. How are things going? Has anybody got a predictor that's getting above 80 or 90% for 3 digits, 4 digits, 5 digits, 6, 7, 8, 9, 10? Awesome. Okay, so there's a number of hands that were still up when we got to 10. So at least combining this data set with this one, it is possible to get a KNN algorithm that will predict 80 or 90% on all 10 digits. For those that have managed to get their KNN to predict well in all 10 digits, how well does it predict?
Relatively well.
Okay.
My problem is just when filming,
yes.
I screw up the hand signals, or I don't have it in front of the lead motion.
Okay.
So I'm wondering, I don't have enough room to get it all. But
there
when
you
I'm
go.
actually doing them right, it picks them up.
It picks it up. Okay, so assuming you can gesture properly, right? Physical context, trying to film and gesture at the same time. So what percent accuracy are you getting?
When I run my classifier, it's 92.8%.
92.8 for about 10 of them?
Mm-hmm.
Is that more or less what other people are getting? Okay, that's fantastic. That's more than good enough. Okay, good to know, because again, this is hard for us to know a priori because we don't have the data. So it sounds like we have a pretty clean data set out there. It's possible. Good to hear. Okay. Any questions about deliverable 6? No? Okay, so let's talk about deliverable 7. So deliverable 7, 8, 9, and 10 are going to be quite a bit different from deliverables 1 through 6. The main difference is I'm not really going to be telling you explicitly what to do anymore. You'll see when you read through deliverable 7 in detail that the instructions are much more vague and it's much more left up to you to figure out what to do. The reason why is because starting in deliverable 7 here, you now have the main engine for your educational software, right? The KNN predictor. So now you're going to start to make some decisions about how to build an educational system around the kernel, which is the KNN. So a lot of design decisions are going to be up to you, and we're going to give you a fair bit of leeway in how to do that. Okay, so deliverable 7 through 10 can be a little bit deceptive because they're much shorter. So deliverable 7 is 3 pages and only 17 steps, but you're going to be doing a lot more thinking per step in 7 through 10 than you did in 1 through 6. All right, fair warning? Okay, so what's the main goal for deliverable 7? So obviously we're assuming now that you have del6.py, which can grab a frame of gesture data and ultimately return back one digit between 0 and 9, which is the user gesturing 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? Okay. We're now going to start to add on some additional functionality building up to a software where a user comes to the system, they log in for the first time. If they're logging in for the first time, they start their learning about ASL from the beginning. If they're a returning user, they log in and they can start from where they left off from before, and so on, right? So that means that we're going to now have to add some state to our program. So in deliverable 7, you're going to be turning your code, which at the moment is stateless, into a stateful program. What's the difference between a stateless and stateful program, for those that have heard these terms before? You may be able to figure it out from this term. What is a stateful program? No? Okay, maybe this is the first time you've heard this. So a stateless program is what you have at the moment, right? It just goes through the while loop and it's in no particular state. It just kind of does what it does every time through the loop. We're now going to add in step 5 here, you're going to be adding in a global variable called program state. This variable is going to be assigned digits, and those digits are going to trigger are going to denote what state the program is in. So you're going to restructure your program quite a bit in step 6 here. Basically, the only thing you're really going to keep is the infinite loop, which you can see in 6a. And every time through that loop, your program is going to reference program state, which will tell which state the program is currently in, and your program will do different things depending in which state it's in. So you plug in your leap motion device, you start up del7.py, and it will by default start in program state 0, which is there's no hand over the device. So as long as there's no hand over the device, your program is going to display something to the screen, and it's up to you what you display to the screen to get the user to do this, right? Later on, when we get into user testing, we are going to judge how good your visualization is by how quickly does someone who's never used your system see what's on the screen and look down at the leap motion device and do this. How long does it take them to interpret your visualization, right? What affordance does it project? It suggests how to interact with this leap motion device, right? One of the most obvious things you can do is play a short video of someone doing this. If that's what you want to do, that's perfectly fine. Images and video is fine. Text is now outlawed. So we're going to assume that the person that's using your system may not speak English at all. So no text to the screen saying, please put your right hand over this little device that's sitting on your screen. You have to do everything with images and video with the idea that it's advertising what the user should be doing. Yes?
If it's like measurements, could you do like 10 centimeters?
Okay, we'll allow numbers. I guess we're going to have to allow numbers anyways. Right?
Just 'cause, like,
that's fine.
that's more global.
Okay, I think we'll allow metric, the metric system. That's all right. Okay, yes, measurements and numbers is fine. You get the basic spirit here, right? Not paragraphs of text explaining what to do. Everything should be very intuitive. Yep.
Do they know in advance that the program is to teach them? Is that not right?
So if you haven't, you've probably sprung this on your flatmates already, but try and find a roommate or someone you know who hasn't seen it. When we get to the end of this, you can do this, right? Just tell them you're doing some homework for your class, put the device in front of them and ask them to test out your system and turn on your program, and if everything's working, they should eventually figure out that their system is trying to teach them sign language for the digit 0 through 9, right? So again, this is a way for you to test how intuitive your interface is. Don't tell your user anything except, I'm making this program for class, can you please test it out, right? And hopefully your program will do the rest, right? That's what we're going to be looking at later in the class when we do some user testing, later in the course when we do some user testing. Sound good? Okay, so as you'll see going through deliverable 7, we're going to gradually add more and more states. And be very careful as you do this. Make sure that you've got the idea about what a state is and how to transition from one state to the other. Once you have that basic logic nailed down, then you can add an arbitrary number of states. So in deliverable 7, you'll get up to 4 states, 0, 1, 2, and 3. Going into deliverable 8, 9, and 10, you can kind of add states as you see fit. That makes sense. Okay, but the first two that obviously make sense is the user's hand over the device or not? The code should be in state 0 when there is no hand over the device, and the moment that a hand is detected over the device, program state, the variable should be set to 1. And now, when you pass through the infinite loop, it skips over this part and enters this part, right? So basically, in the top level of your program, you're still going to have your infinite loop, and you're going to have a growing list of if, else if statements that handle each program state that you have. So far, so good? Okay, so one of the things you want to keep straight then is what are the different states and what events can trigger a change from one state to another. So there's nothing in here yet about state transitions. I've told you what the first transition, right, is someone either brings their hand over the device or a hand leaves the device's field of view. But how do you handle that in the code? Let's start by drawing a state diagram. So for those of you that go into software engineering, you're going to see a lot of these. So let's try and visually represent program flow as being at a state or transitioning into a new state. So here's our state 0, which I'll just nickname no hand. And our second state 1, which is that there is a hand detected. So we have boxes for states, and an arrow going from one state to another obviously indicates that there is some event that causes this state transition. What is that event? Okay, so let's be a little bit more specific, remembering back to deliverables 1 and 2. What actually happens in the code itself to detect that event? How do you know it's happened?
The length of hands increases.
The length of the hands vector increases by 1, right? So let's just say the length of the hand vector suddenly becomes greater than 0. When you detect that in the function called handle state 0, so inside handle state 0, you should have a function that looks to see whether this event has occurred, and if it does, the only thing you need to do is set program state to 1. Right? So inside handle state 0, you're handling events that can cause you to leave that state. So you can see that now in step 7. So here's the body of handle state 0. I've created a function called draw image to help user put their hand over the device. And you can put into that function whatever you want, a video or an image. Line C there, if hand over the device, so you know what's inside that function, it's this, program state equals 1. Pretty easy, right? So let's say we enter this function. We're currently in state 0. We go to line C, and the if clause evaluates, resolves to true. We set program state to 1. We leave handle state 0, come out the bottom of this infinite loop, go back into the top. Now program state is equal to 1, and we do whatever we do while the user has their hand over the device, right? We can obviously, from state 1, go back to state 0. What event is going to trigger that?
Length of handle goes to 0.
Exactly, right? So if the length of this vector becomes 0, inside handle state 1, we set program state back to 0, and back we go, right? So I would highly recommend that you write out this diagram, and you're going to be adding to it as you go, and it's going to get pretty hairy pretty fast. But again, as long as you have the basic intuition about what's happening, the program is running, it's staying in state 0, this happens, we go over here, the infinite loop keeps dealing with program state 1, this happens, we go back here, and so on. At the top level of your code, we're just going to have this flat list of growing if-else statements. Pretty straightforward. So far, so good? Okay, so that's just some hints and tips about how to construct a stateful program. Right? You're going to have this infinite loop, and it's going to be switching back and forth between different states. Some of those transitions may be caused by external events, and some of the transitions may be caused by internal events. So towards the end of deliverable 7, you're going to be adding a new state, which is the user's hand centered? So we're going to try and get the user to keep their hands centered over the device to deal with all these issues about drift and orientation and so on. So we might, for example, detect in state 2 that the user's hand is centered over the device, and we're now going to count to 10. So we're going to see whether we can stay in program state 2 for 10 iterations through the infinite loop. And if the user keeps their hand there for 10 iterations of the infinite loop, we're going to now grab gesture data and send it to the KNN. So the KNN is going to kind of hold back, and it's not going to make any predictions until certain conditions are met. There's a hand over the device, the hand is centered over the device, and the hand has been there for 10 time steps. Okay, so you might add then program state 3, which is where the KNN is making predictions. And you may transition from state 2 to 3, not based on an external event, like something happening with the hand, but an internal event. You might create a variable called timer, and every pass through the infinite loop, you increment timer, and if timer gets to 10 in program state 2, then you transition to state 3. Right? If the hand goes off center, you go back to 1. If the hand disappears altogether, you go back to 0. Make sense? So we're going to kind of hold your hand in deliverable 7 about adding states and which events will transition from one state to the other. In deliverable 8, going forward, you can make up the states as you want and decide what transition events are possible. Can you go from state I to state J? And if so, what's the event that's going to cause it to happen? We talked a while back about making your program visible, right? So that people understand when they're in control and when the program is in control. You probably don't want to be telling the user, the program is currently in state 0. The program is currently in state 1, right? But it should be pretty clear to the user that there are these discrete modes of your program, right? The program does this particular thing when I don't put my hand over the device, and suddenly it starts doing something else when my hand is over the device. So without writing text to the screen, you should be able to advertise to your user that they have done something, or something internal to the program has caused a switch to a different state or a different function. Yeah? If your user isn't aware that these states are changing, things are probably going to get pretty confusing for your users pretty quickly. Okay, that's the HCI side of statefulness. Okay, any questions about deliverable 7? No? Okay, so let's get back to the lecture material. We have been talking about the HCI design process, and we started in last time on talking about information spaces. So in HCI, you're often creating interfaces or hardware-software systems that haven't really existed before, and those systems are going to have unique functions or unique conceptual structures that your user hasn't seen before. How do you advertise that this new information space exists? What's in that space? How do they navigate through that space? So in lecture 9, we're kind of talking about what is an information space. We started by talking about the 3 different kinds of user interfaces, which are 3 different views onto the same underlying conceptual space, which is your operating system. So your operating system is made up of a bunch of conceptual objects. Those objects are called files and folders and so on. And there are different views that have been created over the years to give the user a view onto those information spaces. We ended last time by just talking about tangible interfaces. This is one of the interesting things about HCI, is that a lot of interfaces are becoming more and more physical, or a greater fraction of those interfaces is in the physical world with us. So a lot of interesting HCI systems overlay information spaces with physical spaces. The most obvious example of that is augmented reality, right? You put on your Google Glass or whatever is coming next, you see through the actual glass, you see the physical world, you know about the structure of the physical world, and there is aspects of an information space that is overlaid directly on top of that physical space. Right? Okay. We ended last time by looking at the React table, which is an example of this tangible interface where the user is physically manipulating the physical space, so all these physical blocks that are on top of this interactive table, and then the information space, which is made up of a bunch of conceptual objects as well. Tell me about the conceptual objects that make up the information space in the React table. So in an operating system, there are files and folders. In the React table, there are, I think in the interest of time, I won't play the video again, so remember what we looked at last week.
It's the cubes, right?
The cubes, right? So there were those physical objects, and when those physical cubes were placed onto the table, what happened?
They were linked up to other cubes or other dimensions.
They were linked up to other cubes, right? And if you looked carefully at the video, whenever the cube landed on the table, there's a little halo that was drawn around it, right? So suddenly there is some other conceptual object, whatever that object is, that corresponds in a one-to-one manner with that physical object, right? So that's one particular conceptual object, let's just call it a block, right? And then there were lines that connected the blocks together. So there's a new conceptual object there which doesn't really fit with most other interfaces you've seen. What do those lines mean, the lines that were connecting the blocks? What function or affordance did they advertise?
I don't know if that's what you're looking for, but they were strumming them like a guitar string.
That's right. So there was a point where they were strumming the line. So the lines themselves, you may not have noticed it in the video, but in the center of the table there was a little circle. And in the first block that was put on the table, there was a line that would connect that block to the center of the table. And if there was a block that was placed further out towards the periphery of the table, there would be a line that would connect that block to this block, and the line would continue to connect the nearer block to the center. So as you add more blocks, there are lines that connect the outermost blocks to the innermost ones that ultimately connect to this dot in the center. There's a huge number of visual metaphors that are going on there. What's the main visual metaphor of these blocks that are being connected by strings to this central source? So that central source was supposed to stand in for the speaker itself. So if you put a block and it connects to the source, whatever audio output that block produces ends up coming out of the speakers, right? So it was sort of like thinking about a bunch of rivers that are flowing down into the ocean, right? They're all contributing something to the aggregate audio output of the speakers. What did it mean when one block would be between another block and the source? What do you think that meant then? We saw one block where when you turned it, it was basically a volume knob. What do you think would happen if there was a volume knob here and a particular waveform block that was producing a particular sound further out, and that waveform block connected to the volume block which connected to the speakers? Exactly. It would filter or modulate somehow that sound, right? It would probably turn the volume contribution up or down of that particular block, right? So there's sort of this sequence of blocks, and each one can filter the output of the one that's slightly further out. Okay, last visual metaphor you mentioned, there was points where they strummed the line, right? That's a pretty suggestive visual and auditory metaphor. What was it? What happened when they strummed the line?
Like, I don't know the musical term for it.
Okay.
Sound like a guitar.
It sounded like a guitar, so there was a sound, right, when you strummed the line, but there was also cases where they were cutting the line, right? So whatever aggregate audio contribution this sequence made, if you cut the line, it would silence that stream, so you could focus on the other streams, and then when you were ready to put the original stream back in, you uncut the line, right? All these kinds of intuitive things for a non-intuitive interface, right? This is a novel way of creating music, so they're trying to advertise the structure of this information space. There are a whole bunch of audio sources, so sounds that are being produced, and there is one audio sink, which if you get from a source to a sink, it gets added to the sound coming out of the speakers, right? So there's sort of this hierarchical flowing in towards the center structure to this particular information space. Okay, the reason I wanted to spend a few minutes talking about the React table is I think it's a great example to say, hey, look, there's this cool, interesting interface. It might not be immediately obvious how to interact with it, but we're going to provide a lot of visualization, both visual and auditory, to advertise the structure of this space and how you can create music within it. Okay, so let's back up a little bit, going back to graphical user interfaces, right? They also present structure into a particular information space, which is your operating system. We all organize our graphical user interfaces slightly different. The metaphor has been here for a long time, right? Files and folders that are kind of stacked or heaped or organized in some manner. Okay. There have been attempts over the years to get away from this standard GUI. Most of them have failed miserably. Has anyone seen the Bumptop interface before? This is kind of an interesting one that's been around for a while. It's never quite made it to the mainstream, but kind of an interesting idea. Okay, so the standard information space is still there, right? Your operating system, files, and folders, but they've created now this different view, a different user interface onto it, and they've added a little bit of detail to these conceptual structures. What is the additional detail that's been added here? 3 dimensions, right? So your files and folders now exist not so much in a 2-dimensional space like your desktop. They can exist in 3 dimensions. So there's been a new dimension that's been added to this information space. What else?
I guess you could say the interactivity feels more physical.
Aha. Why does it feel more physical, right? It's not. It's still virtual.
I mean, you're using your hands. You're using actual like muscle movements as opposed to just like keeping your hands stationary.
Okay, so you're actually, touching something on the screen and moving things around, but you can do the same thing with apps on your phone, right, with a touch screen. What is making this illusion that these files and folders are a little bit more physical? What's making that illusion a little stronger?
I don't know, but I mean, it kind of looked like a mess, like my desktop.
Right. So it's still easy to make a mess
Yeah,
in any user
Everything's
interface.
piled up instead of just layered.
Everything can be sort of piled up, right? Because you're in 3 dimensions now. So these conceptual objects themselves now have physical properties, right? Some of them weigh more than others. If you grab one and throw it, it will move and there will be conservation of momentum, right? It'll keep moving until its friction with the ground or other files will cause it to slow down and come to a stop, right? So by adding these physical properties like mass and inertia and friction, it creates this illusion that, yeah, you're working in a more physical space, right? You can sort of throw, lasso things, pile them, shuffle them, sort them, deal them out, and so on, right? Whether you want to use that whether that helps you to organize your files and folders better, I don't know, but it's an interesting idea, right? Taking a standard information space and adding a little bit more structure to it. Okay. Okay, so every time you create a different view onto an information space, you're not only communicating different ways of interacting with that information space, but you're usually drawing on different kinds of organizational themes or ways in which we see the world, right? So Windows and desktops, the WIMP interface has this sort of spatial organization, right? I like to have my email over here and my browser over here. I can panel my desktop. I've got different windows into different parts of my operating system. Menus are helpful because often we want to try and organize things in a hierarchical manner. It helps us to understand a summary of the overall structure. You remember when we were talking about visualizations a couple weeks ago, we talked about the tree map visualization, all those red and green boxes to visualize the economy. That's a way to try and show a lot of information in a hierarchical manner, right? Command-based interfaces, if you like to work at the terminal or the DOS prompt, you like to do things in a sequential manner, right? So in Linux, there's this idea of piping. So you type in a command, and when you type in that command and run it, there's going to be a bunch of output that is either spat to the screen, spat to the web, spat to another computer, or it's piped into another command that you're typing, right? So in piping, you often type a command, vertical stroke, next command, vertical stroke, next command, enter, which is a way of saying take the output of A, give it to B, take the output of B, and give it to C, right? If you're working at a fast pace, it's often helpful to organize things in that sequential manner, right? same underlying information space, operating systems, files, and folders, but different ways of giving you views onto it and different ways of allowing you to interact with it. Okay, pop-ups and notifications, this idea that you want to be alerted of things when they occur, but when they're not occurring, I don't want to see anything, right? Just remind me when this happens. Okay. So different ways of organizing information in information space. So now we get to actually talking about what an information space is. Like a physical space, it's filled with objects and data. People can observe it from the outside or enter into it and navigate through it, right? So most operating system interfaces like GUIs or Bumptop, the idea is you're sort of looking at it from outside and you can sort of manipulate things in it. What are some other information spaces that try and cast the illusion that you're inside the information space? What software packages do you work with where it seems like you're inside this virtual space that the system is projecting?
Apple.
Sorry?
Apple.
Apple, how so?
Whenever you like click on something, it like zooms in.
Right, exactly, right. So sometimes it zooms into the point where it goes past the edges of the screen. Exactly, right? So that sort of makes you feel like you're inside Time Machine or whatever it is, right? First-person shooters, a lot of them you're inside the space, right? When your character turns, the whole space turns in the opposite direction, right? All those kinds of visualizations to say, here's an information space, either your operating system or a virtual world in a video game. You're either outside it, and you can reach in and manipulate it, or you're inside it. You're already starting to construct your own information space around the Leap Motion device. Given the state of your code at the moment when you run it, if you were a new user using it, would they feel that they were outside reaching in or they're inside it? It's a trick question, right? They will be partially inside it. Hopefully they will start to realize that there's actually a physical space, which is the cone of observation above the device, right? The field of view of the device. There's that physical space, and when their hand goes inside that space, they see something on the screen that indicates that the system knows it's there, and their hand is inside, right? They can then move their hand and do things inside that physical space, and also the virtual space that they're seeing in your visualization, right? So in Matplotlib, when you create that 3D visualization, that's the virtual space. There's this virtual cube, and your hand is now inside it, right? You're already starting to project affordances about the structure of this information space. It's three-dimensional, and it's bounded, right? You go too far in any direction, you're outside of it. Okay, so information spaces do not need to be completely virtual or completely electronically. Of course, most of the interesting ones are now sort of layering information spaces on top of physical spaces. Every information space has these two parts, right? The underlying conceptual structure, and then interfaces or different views onto that structure. Hopefully, the views that you create advertise the structure of that space, or only advertise those aspects of the structure that are relevant for what the person is trying to do. Okay, so again, remember we're always creating these information spaces for a particular demographic who want to perform a particular activity in a certain context. So let's take a simple example, catching a train. You can imagine a lot of conceptual structures around that activity, routes, stations, times, railway car classes, and so on. We can have physical interfaces, a paper timetable, or a virtual one like an electronic timetable. Okay. Again, this idea of hierarchy, most interesting information spaces are complex enough that you want to try and layer them in layers of abstraction. The most obvious example here is the internet itself, right? A vastly complex information space, but we all understand the basic structure of it, right? The building blocks of the internet are web pages, and web pages are connected together with links, and all of that all those interconnected pages give some overall structure. I don't know about you, but I don't really know what that structure looks like. This is kind of what that structure looked like. I think this is about 6 or 7 years ago. It probably looks very differently now. But you probably have a general idea about what the structure of the internet looks like. Okay, if we now think about different levels, there are different conceptual structures that exist at these different levels. So at the level of individual web pages, we have text, images, metadata, the structure of the page itself, and then we have different interfaces onto those building blocks, right, onto those pages. So a standard browser, there's different views or different formats, and so on. Then if we go up one level to the level of the internet, there are different interfaces that give you different views onto not individual pages, but snapshots of structure, right? So every time you type in a Google query and it gives you back a list of returns to your query, that's kind of a snapshot showing you the local structure around your keyword, at least from the point of view of Google, right? So a list of search queries or responses to search queries, that's a conceptual object itself. Okay. Okay, so again, in HCI, we're trying to go from this messy world of human needs. They want to do something. Ultimately, we're trying to turn this into a conceptual space or an information space. The React table, the ASL educational system. Okay, so how do we actually do this? How do we conceptualize this domain of knowledge, need, or activity? In order to do that, we have to choose a conceptualization. We have to start to make up conceptual objects for this space. The process of doing that, the process of constructing a new information space, is the process of choosing an ontology or constructing an ontology. So the creators of Bumptop or React table, they said, okay, let's go with the React table. They said, okay, let's imagine that we're going to have this metaphor of things that are flowing down to the ocean. We're going to have these blocks which correspond to different kinds of sound. They can connect together. Their process of talking that through and coming up with those building blocks of their conceptual space, that's them creating an ontology. You've done that already with your ASL system. What are some of the building blocks of your ontology so far? What are some of the building blocks of your software system? So not the code building blocks, not the variables and the methods and the classes. What are the conceptual objects that exist in your system so far?
The hand.
The hand, right? And again, thank Mother Nature for this. The hand is organized hierarchically, right? So the hand is made up of a number of fingers. Each finger is made up of a number of bones. Bones have a tip and a base, and each tip and base has a 3D coordinate in 3 space, right? So that's probably the main conceptual object, right? The hand. Everything you do from now on in your system is going to be built around that. In deliverables 8, 9, and 10, you're going to be adding new conceptual objects, and you're going to get to choose some of them. We're not going to dictate them. Some of the obvious ones are going to be lessons, or tutorials, or lesson plans, or do-overs, or points, or scores, or scoreboards, right? All those nouns are conceptual objects that you may create in your system. Which ones you choose should be based on what the user is trying to do, which is learn the first 10 digits in ASL. Okay, so let's think about how to actually do this. The first thing we need to decide is how many of these conceptual objects are there going to be, right? At the moment, there's really kind of one main one, the hand, and then a bunch of subsidiary ones. Do we want to create 20 different kinds of conceptual objects, or just 1 or 2? Right? Operating systems, there's really, for most users, 2, files and folders. Right? Everything else follows from that. I guess you could count applications as a third one, but there's a relatively few number of them. That's known as a coarse-grained ontology. Right? There's going to be just these 2 or 3 basic things, and the user is able to create them, destroy them, modify them, duplicate them, share them, and so on. In other cases, you might want to choose a fine-grained ontology where you have lots of different kinds of conceptual objects. So let's go back to our example of we're trying to create an information space or an app to help people in a train station. And in that app, we might choose a coarse-grained ontology where we say there is one kind of conceptual object. It's called a train. Any instance of that object is parameterized by 4 things, right? What station it leaves, what station it arrives at, the time it leaves, and the time it arrives. That's it. That's our information space. What's the problem with that? It's a very coarse-grained ontology.
It's really single purpose.
Sorry?
Single purpose.
Single purpose, right? The assumption here, somebody wants to catch a train and all they care about is where does it start, where does it stop, when does it start, and when does it stop. That's it. Does that capture all the things that someone wants to do in a train station? Probably not. What are we missing in this coarse-grained ontology?
The details, I mean, is it a passenger train or a cargo train?
Absolutely, right? That kind of matters for a lot of people, right? So the obvious pro to a coarse-grained ontology, it's simple. Most people get it, right? You open up the app and you see a list of one thing. You have a bunch of instances of this thing called a train, and there are 4 columns, right? T1, T2, origin, destination. Very simple. Great, but if I'm trying to load cargo and I need to make sure I put my cargo on a cargo train, not a passenger train, this app is useless to me, right? So advantage is it's simple. Disadvantage is you miss a lot of the details of the needs of your disparate demographic. Okay, so people care about the type of train. So let's create 4 different categories: express train, first class, cargo, and local, state, or national. So we could start to make up a whole bunch of these categories, which is good, right? Because now it's making it easier for people to find the particular train that meets their needs. What's the disadvantage?
They have to look through a lot more information before they find what they want.
Absolutely, right? So already in thinking about this ontology, we're not going to dive in blind and decide on an ontology. We're trying to pick, to start with just the resolution, right? What are the basic units or basic things that are going to make up this information space? Okay, so few categories if we choose a coarse-grained ontology. It's easy to classify objects, right? When the scheduler gives me a new train, all I need is 4 numbers. I got those 4 numbers, I add them to the app, and it gets sorted into the list. Pretty easy, right? Vague category descriptions, right? Is this a passenger train? Is this a cargo train? Can this particular train take both cargo and passenger? Just missing a lot of detail. And if we start to add that detail in, so instead of having 4 items that describe this element, this object, we might add a 5th one. What type of train is it? We might add a 6th one. How many stops does it have? We might add a 7th one, which is where are those stops and when and so on. We start to make very, very complex objects. The internal structure of any one instance of those objects gets very complicated. Okay, it's the converse, obviously, for fine-grained. Very sharp category descriptions. Every time I get a train, I know exactly which of these categories it should go in because these categories are defined very precisely. Right? Okay. However, sometimes you get into this issue where now it's not easy to actually find the right category because what if a train carries both cargo and first-class passengers? Do I put that in the first-class category or the cargo train category? Maybe I duplicate this instance and put an instance in both of these categories, right? If I want to turn off the ringer on the ringer for incoming text messages, do I go into the text message sub menu or do I go into the notifications sub menu, right? Hopefully in a good interface I could find it no matter which of those 2 paths I choose, but those kinds of issues come up depending on the resolution of the ontology you choose. Okay, so we just got 2 minutes left. Let's pause here for a moment and disentangle some big words. We just spent some time talking about ontologies, right? You're creating a brand new interface for Google Glass, and you're going to project stuff onto the inside surface of the glasses. what are the kinds of things you're going to project, right? You're starting into deciding on what exists. What are the basic things that are going to populate this space that doesn't exist yet? Where are the boundaries between these things, right? Where does a cargo train stop and a first-class train start, right? Do you even have clear-cut boundaries? Maybe you have a continuous information space where certain objects can gradually gradate into another one. Right? So files are files, they're never folders, and folders are always folders and they're never files, right? There's a very clear demarcation between these two things. Once you decide on an ontology, then you can start to construct taxonomies, or in most cases, your users start to create a taxonomy. So all of the laptops that are in this room, they all have the same underlying ontology, files and folders, but we've all created different taxonomies. What would be the taxonomy here in the context of an operating system? What's that? Names of folders. So in my case, at the top level of my hard drive, I have folders called 2006, 2007, 2008. So I organize everything by year, and inside each year there's a teaching and a research subfolder, right? That's my taxonomy. I'll probably continue that until I retire, right? That just works for me. You probably have a different taxonomy. Some of you might have this taxonomy, right? Whatever works for you, it doesn't matter. So if you're trying to remember the difference between ontology and taxonomy, the operating system is a good example, right? We all have the same ontology on our laptops. We all choose different taxonomies depending on how we tend to use our machine, right? So if I'm trying to remember something from last year's class, it's easy for me to go back to 2015/teaching. Right? My taxonomy is organized based on my particular need. Your taxonomy is chosen, hopefully, for your need. Or you've fallen into a taxonomy. Right? Okay. Epistemology, which we won't really talk about anymore, is the philosophical thinking about this process. Right? How does creating an ontology actually happen? Where do these ideas come from? There was no React table before, and now there is, and it's populated with these conceptual structures which didn't exist before. How did they come into existence? That's a topic for the philosophers, which is epistemology, which we won't talk about here any further. Okay, thanks very much. You have a quiz due tonight. You have deliverable 6 due tonight, and deliverable 7 is now available on Blackboard. See you
next Wednesday.
Sorry?
Let's do next Wednesday.
And deliverable 7 is due next Wednesday. That's right.